All right, let's take a look at this particular circuit and I'll show you what the source is here. I've got it set to 25 volts. So we've got a 25 volt source here. I'll write that in as best I can. So V total is equal to 25 volts. Now we know R total is going to be equal to the sum of all of these guys. And I just put a bunch of them in here. It could be 1, it could be 10, it could be 100. So we've got 5, 10, and 20. So let's add that up. 15, 35, 75, 155, 195, 215, 225, 230 ohms if I did the math correctly. So 230 ohms is our resistance. We're going to add that one more time. 10 here plus 10 and 10, that's 20, so that's 30. 70, 150, 230, yes. And this will, I'm going to start at my positive side of my source. That's the long side. This will be R1, R2, R3, R4, R5, R6, R7, and R8, obviously. And now we know that I think I counted more than there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know the sum, each one of these is dropping some amount of voltage, and the sum of those drops should equal 25 volts. So we need to calculate our current first, and we're going to do that by bringing up the calculator. And we're going to take 25 ohms and divide it by 230. And that gives us 0.108 if we round 0.109 amps. So I'm going to say that I total is approximately point, I like to put a 0 in front of them, 0.109 amps or 109 milliamps. So we're going to see if that's right. And the nice thing about Fallstad, just like we'd have to break this circuit and put in an ammeter, we can right click here. Let's see, there's a way to do that. What is it? Let's see, maybe it's scopes or draw. Where is that? There it is. Outputs and labels, add ammeter. So I'm going to click right there. There. Oops, I got it going the wrong way. Actually, I have to break it. So we're going to stop our circuit just like shutting power off. And we'll break this at any point. Doesn't matter. And I've got to break it. I keep forgetting to do that. And this is the same thing we'd have to do in the real world. So we'll hit escape, so I'm not doing that. And I'm going to put my ammeter in as part of the circuit. Now, look at there, 1.108 milliamps, approximately 109 milliamps, or 0.109 amps. And we're going to do that. We can do that pretty well anywhere in the circuit. I'm going to hit escape, and I'm going to break apart again. I'm going to draw sources, add ammeter, run, and see, current's the same. Now, I'm not going to do that for each and every resistor. Actually, I guess I will. We'll do some quick math here. We're going to take 0.109, and by the way, I'm getting that from Ohm's law. Ohm's law says if you draw out V over I times R, well, we had V total, had R total, we needed I, so we covered up the I, and we said we'll divide V by R, we get I. Now, to get individual drops, we want to get the voltage. So we're going to multiply I times R. So we're going to take 0.109, do it times 5, 0.109, do it times 10, 0.109, do it times 20. And we're just going to repeat that over and over and over. So let's bring up the calculator, which I currently closed out. That's okay. Here it comes. All right. So we're going to say 0.109 times 5 equals, and I'm going to put it right here. So this R1, so the V of R1 equals 0.545. That's R1. V of R2, a little easier to do without the calculator. It's going to equal 1.09. V of R3 is going to be double that, because it's 20 ohms. I'm just doing some quick math in my head, but I couldn't do it on the calculator. So let's do it. Let's do 0.109 times 40, shall we? I mean times 20, shall we? 0.109 times 20 equals 2.18. So it's just doubling just because each of the resistors happen to be doubling each time. So 2.18. Got to write a little smaller here. V of R4 is going to be equal to twice that, which is 4.36. V of R5 is going to be twice that one, and it's going to be 8.72. Now, this is where it starts repeating a little bit, simply because we put some of the same value resistors. We got a 40 there, which was the same as R4, 1, 2, 3, 4. So that's going to be also equal to VR6. VR6 is also equal to that. It's supposed to be a 6, but it's a 4 one. Let's see if I can draw that a little better. This is going to be for VR7. This is going to be the same for VR8. And I'll show you what I'm talking about in a minute. And this is going to be the same for VR9. So basically 1 and 9 were the same, 2 and 8 were the same, 3 and 7 were the same, so forth and so on. So let's break out the magic calculator, and we know the sum of those drops should equal the applied voltage. So we'll have to make sure and do some of these twice. We did. So here comes the calculator. All right, so let me get it where we can see clear. There we go. So I'm going to take 8.72, 8.72, that's 5.72, so let's try that again. 8.72 plus 4.36 twice. It equals plus 2.18 twice. It equals, and then plus 1.09 twice. $23.98 plus 0.545 twice. So 25.07 is what we got against the applied of 25, so pretty doggone close. Now we can measure the voltage at each of these. We can insert a meter here. So I'm going to do a output. I'm going to add on, not on meter, but voltmeter. I'm going to put it right here in the middle. And we're going to draw some wires, and we'll measure a couple of these. We won't probably do them all, but we'll we'll measure across the first one here. So I've got to connect it to it. And we'll measure here. And we got 0.543. We rounded to 0.545. Get rid of that last wire. We'll go to this 40, which is the same as this 40, and we said that should be R4, so that should be 4.36. Let's see if that's what we get. Yeah, 4.34 or 4.35 with a little bit of rounding. And we'll even look at the 80 ohm just to feel good about that. So we got a negative 8.7 at 8.72. The only reason it's negative is I've got the positive lead on the more negative side. There is not a it's not a negative voltage in this case. It's just that I've got my lead swapped. I got my positive lead on the more negative side and my negative lead on the more positive side. So that's the only difference. I could reverse those and all would be well as far as positive and negative. So let's do that. There's the more positive side. There's the more negative side, and still get a same voltage. It's just not negative. And these are not connected unless you see a dot, so they're just kind of laying across one another. So we proved Ohm's law. We proved the current, and we've found a way to use Folstad to do that and measure and prove our theory. So that is series circuits, and again, this could be one or two resistors. This could be up to more than 20 or 30 or 100 or whatever. I just wanted to let you see it in practice. And it's a good way to play with this and see, add your meters in, take a look, and add in your current meters, and you can see current flowing and all this good stuff. So it's a real nice tool for seeing things happen virtually.